All right, thank you, Ray. Okay, what are we doing? Tumor growth rate. That's a good way to start out the day. So, the cancerous tumor in the shape of a sphere is undergoing radiation treatment. The radius of the tumor is decreasing at the rate of 2 millimeters per week. So, you gotta remember decreasing and have a rate. So, the radius, so we could say the change in the radius with respect to time, where t is in weeks. Okay, so it would be -2, let's say millimeters per week. We want to throw our units in there, right? Uh, how fast is the volume of the tumor changing? So we want to know what is the change in the volume with respect to time, specifically when the radius of the tumor, so evaluated when R is 10, right? And then they give us the volume of a sphere, all right? So here's our volume. Notice a side note, notice if you take the derivative with respect to R, you would get 4 pi R squared. That happens to be the surface area of a sphere. The derivative of the volume gives you the surface area. Just like the area of a circle is pi R squared, and the derivative of that is 2 pi R, which is the circumference. There's a relationship between boundaries and what's inside of them. So you have these integrals and well, derivatives. You haven't done integrals yet. But we are not interested in the derivative with respect to R. We're interested in the derivative with respect to time. So if we take this, we take the derivative with respect to time of both sides of this equation. All right. Over here, we just have dv dt, again, which I like to call v dot. All right. Remember that dot notation I introduced, the book doesn't mention. On the other side, we have 3 times 4/3, that would be a 4 pi r squared times the derivative of r with respect to time. This is a chain rule. Okay. So that's the derivative, that's the rate of change of the volume at any given time. It depends on what the radius is and what the rate of change of the radius is. So they tell us what this is. Apparently this is constant. So we can just plug this in here and this in here. Okay. So the rate of change with respect to time when r is equal to 10 would be 4 pi 10 squared times -2. This is what, 100. This is -800 pi. Would be, what are our units here? Millimeters. I should have wrote my units in here. I wrote the units. This, radius is in millimeters, and the rate of change is millimeters per week. We're getting millimeters squared, millimeters cubed per week. This is what we would expect for a change in volume with respect to time. Volume per time. Right? So it's usually good to write the units. Okay? They guide us. The book, they don't write the units, but you should write the units. Right? They will guide you, help you follow what's going on. Let's look at another example here. Population growth in the metropolitan area is approximately in the shape of a circle, and the population density is roughly constant throughout. So constant density, all right? Because the metropolitan area is already densely populated, is growing outwards in all directions to accommodate population growth of 13,000 people per year. So we can see that the change in population per time, where time is in year, is 13,000 people per year, okay? So this is simple because they're saying every year you get exactly 13,000 more people. Typically, that wouldn't be the case. Usually, like, you got 13,000 new people this year, you're probably going to get more than that the next year, and more than that the next year. This should actually be exponential function if it's going to be fitting reality, because population grows exponentially. But here they're just giving it a constant rate of growth. Okay. When the radius of the metropolitan area is R miles, its population is approximated by this dude. So we have population approximated with this function. Find the rate of change of the radius, with respect to time when R is 4. Okay. Well, we have this guy. We could just take the derivative of both sides with respect to time. This 5,000 pi is just a constant. Then we have times the derivative of that. So we have times 2 r times the derivative of r with respect to time. This is a chain rule. Okay. So they want to know what this guy is. So we need to solve for that. Okay. So that means dt is this divided by all this stuff. I just want to put that under there. So EP dt, we're dividing by this. Let's see, 5,000 times 2 is 10,000 pi r. So this guy is going to be, plug that in. And plug this in for our r. Oops. So times 4. And then we can simplify. See, I got 3 zeros there, 3 zeros there. I got a 13 over 40 pi. Whatever that means. Some kind of nasty number. Yeah. 13 over 40 pi, it's approximately 0.1. So what does this mean though? It means the change in radius, all right, when the radius is 4 is 0.1 miles. Okay, per year. All right, welcome, y'all. Okay, let's look at another one here. I'm gonna steal their little picture here. Save me some time drawing. Physical science. A woman is flying a kite at a constant altitude. Here's the woman. Here's the kite. The kite stays at the same altitude. So far, the picture makes sense to me. At 120 feet. How fast is the kite traveling at the instant when 130 feet of string have already been let out? So here's the string. We want to know about, they use the letter Z for string here. We want to know when this thing is at 130 feet, how fast is, there we go. how fast is the kite traveling when 130 feet of string have been let out? So here's our string. So when z is 130, what is the speed of the kite? Because the kite here, the position of the kite is given by x. So the speed would be the change in x with respect to time. Right? Again, I like to call this x dot. You can call it whatever you want, but let out. And the woman is letting out the string at a rate of 10 feet per second. So the change in string length, again, this is the string z, is 10. Okay, so when these are happening, what is this? That's what they're asking for, right? They're telling us when the string is this long and the string is being let out at this rate, how fast is the kite moving? Okay, well, we have a right triangle here. Anytime you have a right triangle, which is always, start with the Pythagorean theorem, okay? So the altitude is a constant 120. We use z for string length and x for the position of the kite. So by the Pythagorean theorem, we just get this guy. So we want to find dx dt. Well, we have x's and z's here. Let's apply the derivative operator to both sides. 120 squared. And so if we apply this derivative, let's see. For this, we're going to get 2x, that's the derivative of x with respect to time. The derivative of a constant is just 0. And over here, we get a 2z, and the derivative of z with respect to time. All right? So understand where these are coming from? Because of the chain rule? Yeah. All right. I'll do the trick again, just to remind you. I'm taking the derivative with respect to x. This is 2x times the derivative of x with respect to x. The derivative with respect to time would be 2x times the derivative of x with respect to time, right? This has always just been 1, so you never saw it, right? But now since this is not the same as that, right? Yeah, you have to keep this hanging around. Okay, so we took the derivative with respect to time both sides, we get this. We can throw these 2's away. Okay, so what do we want to know? We want to know what dx dt is. The dx dt at any given time, so you have to divide both sides by x. So I'm going to get a z over x dz dt. So you can see that this is a function of z, x, and dz dt. And we want to know what dx dt is when z is 130 and z dot dz dt is 10. You can see why I like this dot notation. It saves you a whole lot of writing and stuff. So we just plug these in. Let's replace that. Replace that. But what about the x? What do we do there? We go back to this. Okay. This guy here says that, let's see, x, and move the 120 squared over. This is z squared minus 120 squared, square rooted. All right. Well, if z is 130, then I know what x is when z is 130. Does that make sense? So we plug in our z. They say it is 130. Dz dt they gave us is 10. So that's times 10. And now we just need to know what x is. Well, here's what x is in terms of z. So they told us z was that. So replace the x with 130 squared minus 120 squared. And that's your answer. All right, so we had to do a little bit of extra work here. The other problems, we just plug these in, boom, boom. But this time there's like, oh, well, what do I plug in for that? Well, you have the original relationship, and you can use the information to figure out what this value is when z is 130. All right, so it's one extra little step there. Y'all follow that? Not too bad, right? You have all the information you need. And it turns out that's 26. So this is 26. This is feet per whatever the time was. Yeah, feet per second. Okay. These problems, they're usually written where you don't have to write the units down. It all just matches up perfectly for you. Right? But if you're having issues, write the units because the units will guide you. Think about like, well, this is a volume or this is a speed. So it needs to be a length per time, you know. Those can be a really good guide. Okay, here's another one. Physical science. That's all these math textbooks, even though they're not written by business people, right? It's like instead of more business context, they're like, oh, here's a a tumor or whatever. It's like, oh. All right, so we got a little picture here. In a certain automatic coffee maker, hot water passes through coffee grounds in a conical filter and then pours out the bottom of the cone into a coffee pot. However, the cone has become blocked so that no coffee is flowing into the coffee pot and water is rising in the filter. Okay. The shape of the filter is such that the radius of the surface of the water, so it's right here, R, is always half the height of the water in the cone. So here's the height. So they're saying the radius is always 1/2 the height. Let's put h over 2 here. Okay, so that's a given. If water is entering the cone at a rate of 6 cubic centimeters per second, that means the change in the volume with respect to time is 6. Nice and simple. Doesn't depend on the time or the radius or anything else. They made it real simple. It's just constant change in volume. So the water is being poured in at a constant rate. How fast is the height of the water rising? What is the change in the height with respect to time? Specifically, when the height is 2. Okay, so it's all centimeters. Okay, well, we need the volume of the cone. I don't remember that off the top of my head. Shoot. There's our volume. There's our volume. All right. So if we want to find dH dt, there's an h. If we just take the derivative of both sides of this, we're going to get a dv dt. And over here we have this pi over 3. That's just a constant. And now we have the r squared h. These are two separate functions. We're going to have to use the product rule. So we have what? The derivative of the first function. So the derivative of r squared, that would be 2r. The derivative of r with respect to time. That's the derivative of the first function times the second function plus the first function times the derivative of the second function. All right, y'all follow that? use the product rule because you have r squared h, and r squared is its own function, and h is its own thing. Okay, what do we want to find out? dH dt. Here's dH dt. Okay, so let's get this thing by itself because that's what they want to know. So let's see. I guess we'll do it one step at a time so we don't screw it up, right? So we'll have this be equal to 3 over pi dv dt. All I did was divide by that. And then I'm going to subtract this. Boop. All right, and then I need to divide by r squared. So there. I love using this tablet. You know, doing that on paper sucks. Okay. So they say we want to know what this is when h is 2. Okay, so here's h. All right, we know what that is. But what about all these other things? What about the r, the dv dt, the dr dt? Well, they give us r is always h over 2. So, all right, we know what that is. Okay, we just replace that with h over 2, and well, they want to know specifically when h is 2. So we, if h is 2, then r is 2 over 2, which would be 1. Okay, so that's nice. These are just going to go away because they're just the number 1. All right, for this specific thing right here. So now we just need to know what dv dt is and dr dt is when h is equal to 2. Let's see, they gave us dv dt. All right, that's good. We know that one. What about this dr dt? What are we going to do about it? No, let's see. We got this guy. This would mean that dr dt is 1/2 dh dt, right? So if dh dt is 2, so that means that dr dt when h is equal to 2 would equal yeah, that's what's going on. All right, I should have substituted that in earlier. So dr dt is 1/2 dh dt. So we got to take this guy and replace it, which means we got to rearrange our whole thing here. So what we should do before we solve for this, let me substitute it in. This guy's not going to work out for us. This guy needs to be replaced with this, because we don't know what dr dt is. So if we replace it in there, boop, all I did was replace that with this. So now it's all in terms of things we know. Okay. So we want this by itself. We know what all these others are, but this dr dt itself is a function of dh dt. So now it shows up twice. That's okay. We can factor this dude out. So let's just take that dh dt and we're going to factor it out. Boop. Put it all back together here. There. That h right over that. So our dH dt is this divided by all of that. So that would be a 3 over pi dv dt and divided by this stuff. So these 2's go away. So that'd be a RH plus r squared. Right? the R is. They said R was H over 2. So if H is 2, R would be 1. Okay. So if H is 2, R is 1. So dH dt, when H equals 2, R is 1, and they say whether dV dt is 6. So again, derivatives with respect to time, I use that dot notation. It's just easier. So now we just replace everything with what we have. So dV dt, they said was 6. R ends up being 1. They're saying H is 2. R is 1. So what do we get here? We have a 18 over 1 plus 2 is 3 pi. So this would be 6 over pi. All right. So the trick here was what? You take the derivative of your basic formula, you get this guy. And you're like, well, I want this, but there's all these other variables. Some of the information is given outright, right? That's what we're looking for. But you might have to take a derivative of something else. Like if you're looking at it, it's like when you try to plug it in and there's something that you don't know, you're going to have to look up here and say, well, how do I get that information? We needed this dRdt, all right? And that wasn't directly given. So we had to take a little derivative here to get dRdt in the form of stuff that is given. Okay. Well, this wasn't given. We're actually solving for that. But that allowed us to factor it out. All right. So this is, one more step of work. All right. It's nice when they just say, here's everything you need to know, take the derivative, now plug in that information. But that's not always the case. Sometimes you have to look around. Okay. What's that? Yeah, we can't make it so easy, right? Six over pi, 1.9. So when the height of the water of the cone is 2 centimeters, right? They said when H is 2, what was dV dt? The water is rising in the cone at a rate of 1.9 centimeters per second as dH dt, the change in the height per time. So this is about 1.9 cone. Yeah, pi is about 3, so 6 over 3 is about 2. And the units were centimeters and seconds. All right, any questions about that one? Okay. There we go, business one, demand and profit. At a local clothing store, the daily demand for a certain brand of blue jeans is given by P equals 200 minus 2x, where P is the price and X is the quantity demanded. Excuse me. The cost of purchasing these jeans at wholesale is $25 per pair. Ignore any fixed cost. The cost of purchasing these jeans, okay? Business jargon always gets me, right? It's like, is that the price or is that the cost? Right? Well, it's both. Depends on if you're looking at it from the consumer point of view or from the manufacturer's point of view or, from the retailer's point of view. Anyhow, this is something we have to keep in mind. If daily demand, all right, so this is X, all right, for this brand of jeans is currently 35 pairs of jeans. So X at time 0, which often is written X sub 0 or X naught, is 35, okay? And all right, the cost of purchasing these jeans at wholesale, I think that would be price, P. So we'll say P is 25, right? All right. Daily demand is 35 pairs and declining by 2 pairs per day. So the change in demanded quantity as time passes is 2. Okay, that's the given information. How is the profit changing? Oh, wait, is this price or profit? Okay, well, lowercase p versus capital P, they look a lot alike. So I'm going to do a little squirrely, like that's my profit, right? Instead of like price, just to keep the lowercase and the capital separated. What is the profit? The profit is revenue minus cost, right? Okay. And revenue is the price times the number sold, right? And we're selling exactly how many are demanded, apparently, in this ideal world. And then the cost, they said, was 25 per pair. I'm still getting confused with this price. Is this the cost or the price? This is my best guess right here. Let's see what they got. This is confusing me. See if I was remotely close here. You must determine an equation that relates profit and the quantity demanded. Profit is the difference between revenue and cost. We must find the revenue and cost functions. The revenue generated by selling X pairs of jeans is the price times the number. All right, yeah, X times P. That was good there. And they gave us P to be this, so you just substitute that in. All right, that was good so far. Is the cost function that was confusing me? Is that just what they gave us? Let me see here. These are costs. Right? The cost, yeah, 25x. All right, I was on the right track. Sure. Okay, so if you plug in P, right, then we'll get a profit function. So here is our ultimate profit, right? This is profit. Okay. And what do they want us to do? How is the profit changing? All right, they gave us this information. Let's keep that over here so we don't lose it. This is what was given. They want to know what dp dt is. Well, take the derivative of that stuff. So this would be a 175 dx dt. 2 times 2 is 4 x dx dt. Okay, which if you wanted to, we could factor out this dx dt. This would be 175 minus 4x times dx dt. So they want to know what this is when all of this is true. Okay, so the dt when x is 35, right? Because we're going to need that. And dx dt, or x dot, is 2. We have a 175 minus 4 times 35 times 2. And just plug that in your calculator at that point. And what number do we get out of here? I wish this thing would just autocomplete, like, it just read my handwriting and be like, here's the number, right? That would be great. What do we get? 70. Boop. So this is dollars, this is time. So whatever the units were, I guess it was days, if we read the paragraph, you know, make sure we follow the right time. All right, so the change in profit is $25 or $70 per day when the demand is 35 pairs of jeans and dropping at 2 pairs per day. Oh, it's decreasing. This is a negative number. Boop. Right? This is bigger than that, so we're going to get a negative. it's important to make sure you don't lose those minus signs, right? And when you read the paragraphs, it's easy to overlook the word decreasing or increasing and just look at the number and write the number down. Make sure you pay attention to decreasing. So you can put that minus there, okay? Like here they say, where did it go? Here's the problem here. Declining by 2 pairs per day. This, the minus right there, I forgot that. Yeah, so this should have been a minus. This should have been a minus. Really easy to miss that when you're reading these paragraphs. I do it all the time. And we're skimming the words, trying to look for the numbers, right? All right, that's it for 12.5. So we still have a few minutes left. We can go back and work some of these checkpoint problems if you want, or if you have specific questions about any of the homework problems, I can work some of your homework in here. Have y'all started doing the homework yet? Yeah, any of y'all stuck on any particular problem or anything? No, y'all, we've mastered it. I can do them all in my sleep. Let's see here. Where is assignments? I'll pull up. I mean, I could do the textbook problems, but you'll probably prefer if I did the actual homework problems, right? Let's score. Good thing I came in on Friday. All right, let's see. This is section 12.5. All right. Why are these all out of order? Oh, I see. It's like 159. I'll pick one at random here. Let's look at number 10. All right. This is number 10 on your homework. Suppose that the price P in dollars in the weekly sales in thousands, so we have dollars and thousands of units of a certain commodity satisfy this demand equation. All right, I'm going to write that down. 2p cubed plus x squared equals 275. Determine the rate at which cells are changing. The change in cells. S. Cells. All right. I'll have to figure out what S is in it. Which cells are changing at a time when x equals 5 and p equals 5, and the price is falling. So change in price with respect to time, it's falling. I don't want to forget my minus sign at $0.2 per week. So we're talking about weeks, dollars, and X's in thousands of units. All right. So when they say the change in cells, what do y'all think they mean by S? Cells. That would just be revenue. Is that what they really mean? Cells, right? It's like money coming in. Y'all are the business people, right? I mean, it's a simple question. What's sales, right? But everything we've been like taught has been revenue, price, profit, cost. What exactly do they mean by sales? Y'all have to tell me. I'm not a business major. In the con. So it's revenue. Well, we know that the profit is revenue minus cost, right? But what do they mean specifically by sales? To me, that means revenue, right? For my year I spent working at Radio Shack, what are the sales for the day? It's the price times the item, added up. sales is the number of units being sold, not the price. Okay, so then that's revenue. So your sales is just the number of units sold. Okay, so that would be X. Determine this specifically when this. So if these are true, then what is that? Okay. So now we have the question understood, right? Answering it's going to be easy. Now we know what the question is. Okay, so they gave us this. We need to find an expression for that. We could do implicit differentiation, but you know what? We could just do this first, right? And then we're not interested in a negative number of quantity, so I can just square root. We don't have the plus or minus here, because we're only interested in positive x. So we don't have to do implicit differentiation here. We can get the x by itself first. And now, take the derivative with respect to time. So this is 1/2 power, right? So 1/2, subtract 1 from the exponent. Now multiply by the derivative of stuff on the inside. 3 times a minus 2 is a minus 6. P squared, dp, dt. So to figure out what this is, when this is true, we would just plug in, let's see, P, dp, dt, P. We have the information we need. So this one was really easy. We didn't even have to do implicit differentiation. We could solve for x first. The hardest part of this problem is figuring out what they mean by cells. Any questions? All right, let's look at another one. I'm not gonna do the whole thing for you. Let's see, what was that? 10. Look at number 12. Oh, there's a question. Where's the column go? 12. The volume of a cantaloupe. All right, so if you're a cantaloupe salesman, this is relevant. This is just the volume of a sphere. Okay, the radius is growing at a rate of 0.7. So the change in radius with respect to time is a constant 0.7 centimeters per week. At a time when the radius is 7.3. So this is not true. The change in radius is different at different times. This is specifically when R is 7.3. Okay. So I would write this as R dot evaluated at 7.3 is 0.7. That's how I would write that down. But because it just looks better like this. This looks like I'm multiplying or something weird. So R drdt is a function of R, but specifically at when the radius is 7.3, it's 0.7 here. How fast is the volume changing? dV dt equals what when, at that moment, when R dot or drdt is 0.7. Okay, so we have this guy. We don't have to do implicit differentiation. The b is already by itself. So if we take the derivative of both sides, dv dt, 3 times 4/3 is a 4. Subtract 1 from the exponent and multiply by the derivative of r. Okay, so dv dt, when r dot is this, well, you plug that in there, and they say dr dt is 0.7 when r is 7.3. So they gave us exactly the information we needed. We just needed to take a simple derivative and plug in the information they gave us. So that one's really easy too. Questions? All right, when I'm going through the stuff in the book, nobody has questions. When I'm doing the homework, so what's the answer, right? Okay, we have time for another one. Number 14. Didn't I just click on something here? Click on it twice. Well, we have an exam coming up, don't we? Next week, right? Wednesday? Yeah. Wednesday. We have an exam on Wednesday. Okay. Oh yeah, we have all that retry mess. I'm gonna have to think about all that. In order to do the exam retry, we're having a meeting today about it. You have to have at least like an 80 on your homework average, something like that. If you don't have an 80 on homework average, you can't take the exam retry. Okay, keep that in mind. Do your homework. Can't you just keep doing the problems till you get them right? Basically, isn't that how it works? So y'all should all have 100 homework averages. It doesn't go away till you get 100. That's cool. I like that way better than the old days, man. It's like you get one shot and that's it. Suppose that for a company manufacturing calculators, the cost, revenue, and profit equations are given here. Great. The production output in 1 week is X calculators. So what is that? Change in production. Production output in 1 week is X calculators. So X calculators per week. What is that? That's going to be the change in something. That's a derivative right there. We need to write that down. What is that? The quantity, right? Well, X is the quantity. Let's move on. We'll come back to that if we need it. The production is increasing. The production is 1 week per, in 1 week is X calculators. The production is increasing at a rate of 400 calculators per week. What is production here? This is change in production. We need a letter for production. I see cost, revenue, profit. Which one is production now? With production output. Production is increasing at a rate of 400. I don't want to use P for production because that's profit. So again, this is a problem like the cells. Like I don't know what they mean by production here. Which variable is that? Well, we have X. We only have X, right? It's not cost, it's not revenue, it's not profit. Is this under the assumption that we're producing exactly what is demanded? Because in this class, things are weird. It's like the cells are always exactly how many is demanded. We always sell exactly how many that's demanded. We always manufacture exactly the number that was demanded. And we sell exact, you know what I mean? So they're all the same thing in here. But to me, they're different things, right? Production. Well, I'm going to use squiggle for production here. So the production output in 1 week is X calculator. So production per week is X okay, this is where they're defining production. Production is X. All right, so there we go. When they say production, they mean X. That's what they meant by that. They're telling me what production is in that sentence. Can't be any more straightforward than that, right? Production is X. Okay, so production is increasing, so the change in production with respect to time is 400 calculators per week. Not always, that's only true when the production is 6,000, okay? So dxdt is a function of time, it's different all the time, but when production is 6,000, the change in production is 400. Find the rate of increase or decrease in cost. So the change in the cost with respect to time, rate of increase, cost, revenue, and profit. So cost, revenue, and profit. So all you need to do is take the derivatives of these, right? This one would be 300 dx dt. So dx dt is 400, just plug that in. This one would be 300 dx dt minus 2 over 20 x dx dt. So here, take the dx dt, which is 400, and your x and plug it in. That's r. And then this one would be, since it's r minus c, this would be, what we want. What do they want? dp dt. So since p is r minus c, this would just be dr dc. And we know what those are already. Just plug those in. Boop. Boop. There you go. And there's that one. Questions? All right, let's get out of here.